So anyway, welcome to Untangling CSI, powering persistent storage for KubeVirt. I'm Brenda McLaren, and this is...
My name is Chris Keller.
We're both associate principal solution architects at Red Hat, and we're here to talk CSI. So thanks for showing up to let us speak. So Kubernetes made compute really easy, right? It's agile, it moves from node to node, it can scale. But storage, it brings complexity to the party and requires layers of abstraction. Each vendor has their own container storage interface, CSI driver. And of course, they're all not the same, and they all don't behave the same. And then you add KubeVirt into the mix, and you're running virtual machines on top of Kubernetes. You're not dealing with container storage anymore, and it brings just a lot to managing that storage. You have to start dealing with more latency issues. You have to make sure that snapshots are supported. You have to make sure that read-write many is supported for the live migrations to work from going from node to node with your VM workloads. And so all of that's layered on top of CSI. So now you're kind of stuck in the middle of a cornfield, like just with your data waving a red flag, you know, saying, here I am. So what is CSI? In a nutshell, it's the universal translator between Kubernetes and the storage provider. And it's not going to matter who that storage provider is, right? It doesn't matter if it's a storage array that's sitting on a SAN, NAS, software-defined storage, or even a cloud provider. They all have that CSI driver. So instead of every vendor reinventing the wheel and Kubernetes having to try to understand every proprietary system out there, CSI gives us the consistent way of managing the storage through the standard API, regardless of the provider. Another big win is that storage is provisioned very dynamically. So when that volume is needed, that's whenever it's created. So CSI is, actually the call goes to Kubernetes. Kubernetes is going to actually look at that definition of the volume that was requested, and it's going to send it to that storage provider, and that storage provider is going to create that LUN on that storage array, or that volume on that NAS filer, or like the volume within the software-defined storage. It's going to create it on the fly and get that provision to the worker node that workload is scheduled on. And it's all done, like under the covers, all very transparent. And then also it handles all of the life events of that volume, right, in its lifetime. It handles the resizing. You want to resize a volume, CSI is going to handle that. You want to snapshot it or clone that volume, CSI is going to handle that. And then whenever you no longer need that volume, it's going to clean up after you. So in short, CSI turns storage from an administrative nightmare to a plug-and-play system for Kubernetes. So if we rewind a little bit and go pre-CSI, each storage vendor had their specific Snowflake type integration baked into Kubernetes. And that was actually known as what they call in-tree plugins. So it actually was inside of Kubernetes. So if there was a Kubernetes update, then everybody had to take that collective hold your breath and hope that nothing on the storage broke, because you're trying to fix something for one vendor which could break another vendor. So, and to make matters worse, the plugin actually ran within kubelet with elevated privileges. So security and maintenance is like another nightmare. So CSI was introduced like earlier than, obviously they didn't want it GA, but it went GA in version 1.13 of Kubernetes, which was like December of 2018. And it kind of turned that storage integration upside down. So it said, okay, well, we're going to come out with out-of-tree plugins. So now it's no longer part of the Kubernetes core. And we're just going to have these gRPC API calls that are going to be standard that lets Kubernetes know how to talk to each of the CSI drivers. So now they're all playing consistent. There's no more special snowflakes out there. They're all talking the same. And then a big win was that Kubernetes can now upgrade independently from the vendors, and also each individual vendor can update and roll out their features and capabilities as they need to as well. So now chaos is turned in to be predictable, and we have consistency through standardization.
So when we look at CSI drivers, if you've ever installed a CSI driver on a cluster, you take an operator from a vendor or a Helm chart, customize, whatever. You're actually installing two components. There's the CSI driver, which we collectively refer to as the entire bundle, and then there's a set of, the drivers are obviously provided by the vendor. And then we have a set of sidecars that exist within various components of the packaging that are provided by SIG storage. And these sidecars are basically abstractions and work with the Kubernetes API and act as a bridge between the driver and the API. So when we look at the vendor-provided components, we're really looking at two core areas for the drivers. We have the controller plugin, which is going to handle the actual provisioning on the backend storage. So these are the API calls that we're going to make to the storage head to provision a LUN, like Brenda was talking about earlier. We also have sidecars that are going to handle attach and detach, resize, and snapshots, and things like that. When we refer to attach or detach here, we're not talking about actually mounting the particular volume to the node. This is still at the API level, but think more, I guess from a SAN standpoint, this would be where the volume is actually granted access to the node. So on the controller side, we allow that particular volume to access the node where that storage is going to be mounted. So think of volume binding and that type of thing. The node plugin is what's actually going to take that LUN and mount it directly to the node and potentially format it if it's of type file system and do that integration on the node side. So aside from like the external provisioner and attacher and those types of things, there's also a node driver registrar. So this component is going to run on the node, and that will actually register the driver with the kubelet. And then there's some other odds and ends in there too that work to collect metrics and do other things. So from a very high level, if we look at this deployed on a cluster, this is an arbitrary cluster. I just have 3 nodes up there, but could it be, any? Basically, across the bottom, we've got our control plane to the left, nodes here. We have the kubelet is obviously deployed on every node. And then we have the CSI node components, which are typically deployed as a daemon set. They're going to be, basically running on every single node that's within the cluster. You could limit that to a subset of nodes if only a subset of nodes needed access to that, but typically it's cluster-wide. And then above that, we have the controller, where most of the sidecars live and where all the integration with backend storage happens. These components, I have them listed on worker nodes. More recently, I'm seeing them deployed on control plane nodes. Different vendors do different things. But really, the main point is that that controller, which is typically a deployment, I only have one pod listed here, but it's usually replicated. Those components can really live anywhere. So from a flow standpoint, there's a lot of API calls that happen. There's a lot of back and forth here. So when we look at a flow, hypothetically somebody creates a persistent volume claim. If you look at a PVC manifest, there's references to a storage class and the size of a volume, whether or not it should be of type block or file system, all those different types of things. So the external provisioner is actually monitoring the Kubernetes API, and every time it sees a persistent volume claim that comes in, and the storage class or other metadata matches the values it's looking for, basically this is a PVC that I need to handle, it'll grab that and then reach out to the controller, which will go and affect and create the volume based off of the requirements in that PVC and the settings in the storage class. So once that's created, we have the volume attach and detach, which could occur if a deployment was created that referenced that or a pod. So at that point, we have the external attacher go in and attach that volume to the node. There's sidecars on the node portion that will actually mount and load everything onto the particular node where the workload is going to live, and so on and so forth. So again, like to reiterate, the controller plugin, that's where most of the sidecars are going to be. Those are monitoring the API server, and again, are acting as that bridge to the controller and other components. And that's really where the kind of the delineation is. And then to Brenda's earlier point, kind of separating like the in-tree and out-of-tree components, everything to the left of that dotted line would be considered, in-tree. Technically, I don't think the sidecars are directly in the Kubernetes source, but they're maintained by the Kubernetes maintainers, specifically SIG storage. So when a vendor ships the actual container or the driver package, in effect what they're really doing is pulling the source code and then recompiling it, potentially modifying it to suit their needs. But every driver is going to include that, at least baseline configuration from SIG storage. So if we look at this from we're looking at the flow high level from Kubernetes standpoint, but like the practical application of this is, you have a cluster administrator that's going to set up the CSI provisioner and storage classes. So that's basically the installation of the CSI driver. By default, some drivers will install storage classes and do the last mile configuration. Other vendors may make you do that last mile, create your own storage classes, volume snapshot classes, all that kind of stuff. But ultimately, that's left up to the administrator. And then you have a storage consumer that can view storage classes and make persistent volume requests based off of that storage class. So the provisioner, if we look at kind of the third phase here, is actually going to make the API call like we discussed, and then it's also going to set up the persistent volume and persistent volume claim resources within the cluster. And then after all that's done, when the VM or the container finally gets scheduled, the provisioner will attach that to the node.
Thanks. So we have like we'll talk about two separate worlds of storage, right? There's the traditional legacy enterprise type storage, and then you also have the software defined storage. And even though they're two completely separate different worlds, they have the common friend in CSI, because again, CSI sets the standards. If you want to use your traditional enterprise array that has the rock solid block performance, it's predictable with its latency, you have all your infrastructure already in place with your HBA switches and fiber channel cabling, you're ready to go, right? CSI is going to take care of the messy part, the administration of those volumes, to be able to provision the LUNs, map them to the host, and from a Kubernetes standpoint, to the workload, to the user, is all seamless, right? And you don't have to go through and like contact the storage administrator to provision the volume. That CSI driver is taking care of all of it. You want to take a snapshot, CSI is going to take care of it. You want to clone it, again, CSI. On the other side, you have software-defined storage. You have no more of that like big black box, but rather you have software that's running inside of Kubernetes, just alongside of your application workload. It's going to scale like your workloads. It's going to upgrade like your workloads, and it's going to be self-healing. So in the case of failure, whether that be like node failure or drive failure, You're going to have either replicas on the software-defined storage aspect, or you're going to have maybe erasure coding. And then, again, CSI is the one that's going to handle the provisioning. So it's two very different solutions, but a common, consistent interface with CSI. And then you have the other two worlds meeting of containers and virtual machines running on Kubernetes thanks to KubeVirt. Same storage model. Doesn't matter if you're looking at pod workload or you're looking at VM workload. Behind that is going to be your PVC that can either have block or file storage based on the CSI's capabilities. The other thing that KubeVirt does add, like on top of that PVC, is what we call a data volume. And that data volume is actually what's going to specify where to get that base OS image from. So are you going to clone it from another PVC? Or are you going to download it from a URL? Where's that base image coming from? So that data volume sits on top of the PVC. Let's see, what else? A key feature that is required for your VMs is the ability to have a read-write-many volume. So in Kubernetes terms, or storage terms, it's read-write-X for read-write-many. Not to be confused with like clustered file systems where you're reading, writing from multiple pods or worker nodes at the same time, but it gives you the ability to actually mount that volume on two different worker nodes at the same time, so that live migration of the VM can occur. But the CSI is handling all of that, right? To be able to say, I'm over here on worker node A, but I want to move over here to worker node C. That CSI is going to make the calls to map the volume over here. That memory migration is going to happen for the VM, and then once that's done, it's going to unmap that volume from over here on worker node A. And again, that's all seamless to the workload, to the user, to the administrator, et cetera. And then under the hood, whenever it comes to actually kind of like what Chris touched on, is that when it actually, like the CSI is going to handle the mapping on that backend provider, but kubelet and the CSI node plugin are going to actually get that mounted inside the pod correctly for the either container or the VM to be able to use that volume. You also get universal observability and administration. It's the same storage metrics, same automation, whether that's across containers or virtual machines.
And so when you're going through and evaluating a CSI driver, Brenda and I both work for a national pre-sales team, and we focus mostly on KubeVirt. And we deal with a lot of customers that are doing VM migrations, and storage integration is paramount on top of networking configuration and integration. So when we talk to customers, we've kind of come up with these 4 like common pitfalls that you really need to be aware of when you're selecting this or planning to do this type of integration within your Kubernetes environment. So I think the first one is kind of treating all CSI drivers as equal. Maybe 2 years ago, CSI drivers were terrible. They were bad. And then, recent industry events have precipitated a massive shift of enterprises to KubeVirt. There's a lot of KubeVirt adoption now. And because of that drive, a lot of the vendors got their act together, and now most of the drivers today are pretty good. But there are big differences between all the vendors. So I think across the board, obviously, volume lifecycle in terms of creating a volume and deleting a volume, even snapshots at this point are all integrated. But I kind of alluded to this before. There's varying capabilities, whether or not the drivers support, or the installation anyways, does the last mile config, pre-wires the storage classes, and does the snapshot integration, and all those different types of things. The other thing is ignoring performance tests. So when we look at virtual machines, at least for a baseline I/O, establishing that pattern with a block device, I think everybody has the tools and the capabilities to do that, and there's well-established patterns for that. The I/O tuning, at least at the operating system level, is going to be pretty consistent with what you would expect on traditional bare metal or on existing virtual workloads. But one of the biggest things that you have to look out for, aside from just the baseline I/O testing, is a lot of other ancillary stuff that most people don't consider when implementing something like this. And a lot of it has to do with API and scalability. So the rest of this is kind of at massive scale, but if we look at traditional virtualization, like we'll use VMware for instance, because they're the king. When you look at the disk mapping for the individual virtual machines, it's a one-to-many mapping between the data store and the virtual machine. So you have a contiguous LUN. It's presented to all the nodes, and there's a clustered file system laid on top, VMFS. And all the virtual machines are put into a contiguous block of storage. It's the opposite in KubeVirt, Kubernetes in general. So with an array integration, for instance, if you're doing direct integration with a SAN, every one of those virtual machine disks is going to be a LUN. So if you've got 500 VMs with 2 or 3 disks each, that's thousands of LUNs that you're going to be presenting across all the infrastructure within your environment, whereas before you were really only presenting a couple. So you have to take into consideration now, especially with dynamic provisioning, because we have the controller and users requesting volumes, deleting volumes, and traditionally in SAN, especially when you're working with like a database or something, most of that stuff is static. When you initially deploy the server, you do all the zoning, you allow the LUNs in, and that's kind of the end of the configuration. Maybe once a year you add a LUN, the database grows, stuff like that. But when we look at this in Kubernetes, if you have a use case where you're provisioning, 30 or 40 virtual machines at a time, I have customers that do more than that. If you think about the API requests that are made for each one of those virtual machines and each one of those disks backed by the virtual machines, between the sidecars, monitoring the Kubernetes API, making requests to the controller, the feedback loops, if you don't tune the Kubernetes API, if you don't increase the expected queries per second, the burst rate, if you don't scale the controller to potentially handle the scale of the API integration, those are all pitfalls that you can run into, and they can cause significant issues, not in terms necessarily of performance and disk I/O, but unhandled patterns with your automation. You don't catch the right error conditions because of timeouts. Volume attach and detach times to get the SCSI bus potentially rescanned because you're adding more LUNs, the amount of time that takes. And this is moving back and forth between nodes too. So if you do a live migration, may trigger another rescan. So all those different things you have to consider.
Yeah, also backup and failover, right? Replication isn't backup, and snapshot isn't going to be a valid backup either unless you move or copy that off of the cluster. Make sure your snapshots are crash consistent. The QEMU agent that runs inside the VM is your friend. Make sure that also you have defined RPO and RTOs. Stay current with your CSI drivers. Like Chris mentioned, there's been a lot of changes, new features, capabilities that have been introduced and are constantly being introduced within CSI. So you want to make sure you read the fine print and make sure you know what versions of Kubernetes your CSI driver supports, because you don't want to be caught, upgrading to a version that's not supported, or upgrading Kubernetes and not having your CSI driver support it. But definitely stay current.
And so to kind of recap, when we're looking at key capabilities, I think probably dynamic provisioning is number one. I mean, that's the whole intent of the storage integration, is to create and potentially destroy a volume that you're working with. When we look at snapshots and clones, that's going to be another key integration point. let's see. Go ahead.
Yeah. So to make sure that that if you're looking at topology aware, to be able to have zones like either defined across different zone environments or locations, or even if you do within racks, that your CSI driver can support that topology aware through the labels within Kubernetes. You can also look at, make sure that you're aware of the HA availability and failover. A lot of like software-defined storage, they're going to have the replicas that are available to protect you against the node failure or the disk failure, but then you also want to make sure that you're not, like going across, like the switches, or you want to be able to have that data local. And then there's also performance testing, right? There's some CSI drivers can support I/O settings within the storage classes that can define the maximum IOPS and bandwidth that a volume can consume to deal with that noisy neighbor. You can also tune the performance a little bit within the CSI by indicating how many replicas that you're going to keep of the data as well. When you're looking at file system, different file system types and mount options are going to give you different performance as well. So like going back to what we said before in pitfalls is test, test, test. So if, kind of clearing the fog here for you is that just know that CSI is it's the backbone of Kubernetes storage, right? It standardizes how we handle storage for all the workloads, whether it's container or KubeVirt VMs. It decouples Kubernetes from the vendor-specific quirks through the gRPC interface, and it allows us to make storage as agile as your compute within Kubernetes.
And I think if you guys take away anything from this, is really when you're comparing different CSI drivers. If you have a strategic direction to re-platform to KubeVirt, if you're lucky enough to be in the middle of a refresh for your storage, it might be awesome. But it's very difficult to migrate away from something as embedded as storage can be. So if you're planning on implementing KubeVirt, definitely check out the capabilities that your vendor has for the integration. Most of the baseline capabilities are going to be there, again, like the volume, lifecycle, snapshotting, and things like that. The ones that aren't there yet will catch up pretty quickly, but you really still need to do the homework to make sure that all the capabilities are there. And then I think obviously run the latest after testing and validating to get it into production. So from a roadmap standpoint, I think probably the biggest thing is change block tracking, but I'll let Brenda get into that one. I think, so this is less to do with CSI. I think it has most to do with the protocol integrations and modifying the drivers to include this capability. But a lot of customers and a lot of vendors are interested in starting to support NVMe over fabrics and those types of integrations. So I know of a couple of vendors that are supporting that today, but we're seeing a lot of customer demand for it. So I would expect that any of the storage providers that are offering this capability, if they don't have it in the drivers today, it should be in there pretty soon.
Yeah. Look for replication extension coming from SIG storage to make your multi-cluster DR vendor neutral. And then the other big one is change block tracking, right? Is to be able to support that incremental backup and not have to take a complete backup of that entire snapshot of the volume. So change block tracking is defined within the KEP 3314. But it is going to be CSI like vendor dependent, right? Or it's going to be implemented at the CSI driver level. So you keep current with your drivers, talk to your CSI provider to see when they'll have that integrated into their driver going forward.
The CBT stuff, like the cross-cluster stuff is, I don't think that's necessarily a change in CSI. But the CBT is a change. Like there's additional APIs that are being added. There's an additional metadata service And the exposure is different too. Like the metadata services that exist inside CSI, like there's the node registrar and then the identity service that shows like supported versions of Kubernetes and some other capabilities. That will be consumed by your backup providers. So the current integrations is with the backend storage and Kubernetes API. But this will be another integration point in a separate metadata service that'll handle that specific integration.
Yeah. So with that, thank you.
Any questions?